Hi, my name is Reese and I am part of the Managed OpenShift Black Belt team based in EMEA. Today we're going to work with the Red Hat OpenShift Data Science, running on our Red Hat OpenShift on AWS ROSA managed service. Red Hat OpenShift Data Science is an open source machine learning platform for the hybrid cloud. By providing a fully supported environment to establish ML Ops best practices, it means data scientists and developers can rapidly train, deploy and monitor ML workloads and models on-premise and in the cloud. Today we have already set up our ROSA cluster, but then we will install the Red Hat OpenShift Data Science operator. We'll then access the data science console that creates. We will then configure a Jupyter notebook and pull in the code required for the application we're going to work with. We'll then use the Jupyter notebooks and TensorFlow to explore a pre-trained object detection model. Then we'll serve that model in a REST API as a Flask app. And then we'll take that Flask app, we'll use source to image to be able to build it properly and deploy it. Finally, we'll take a front end, we'll build that, we'll deploy that to allow you to show off your model to the world. Let's get started. So we have our ROSA cluster. Let's click on Open Console. Let's log ourselves in. I'm already in. I've just checked that this cluster is up and running okay. You would normally set up HT password with the cluster admin initially and then set up your IDP to allow your users to access it how they need. So we need to install the data science operator. So we'll click on the operator hub and we will do Red Hat OpenShift Data Science, and that brings up the operator that we need to install. Click on that and it gives you some information about what it is, how it works, the latest version, the capability level, who supports it and all of that kind of stuff. Click on install. It brings up the install window with bits of information, the channel that you might want, the installation modes. We're just going to follow the default here, so we're going to click on install, and this takes anywhere around 5 minutes normally to install. So let me cover what is Red Hat OpenShift Data Science. It is an open source machine learning platform for the hybrid cloud. It is fully supported environment built to allow organizations to establish best practice ML ops that will allow their data scientists and developers to rapidly train, build, deploy, and monitor machine learning workloads and models on-premise and in cloud. We're obviously using it out in the cloud. It's part of the AI-focused portfolio that is Red Hat OpenShift AI that provides tools across the full life cycle of AI and ML experiments, models that your organization might require. We'll jump back as soon as this is finished installing. Okay, our operator is installed. This is what you kind of see. Installed operator ready for use. Click on view operator. Once again, it shows us a few more details, namespace, labels, when it was created. If we go into administration, one of the important things we can see if we scroll all the way to the bottom, it's added a few namespaces for us. Red Hat ODS applications, monitoring, the operator that we selected, the namespace we selected right at the start, and also the Red Hat OpenShift Data Science notebooks. So how do we access this? If we click on this icon up here, you'll see OpenShift Managed Services, and we've got the Red Hat OpenShift Data Science there. Boom, login. As you can see, it gives various applications. We've got the Jupyter Notebook, which is installed by default, but as you can see, there's various other tabs under here, data science projects that your team would share and work with together, models that are being served that a team could put up and allow others, resources. As you saw with the operator hub, we have something very similar. With a marketplace that allows you to install tools, processes, and various other things in machine learning and data science areas that are useful to help you accelerate the way in which your teams can deliver these models and these applications to allow your business to gain more value from using this. So we're going to jump back to what's enabled and we are going to launch the application. As you can see, there's various options for the notebook image. You can create custom notebook images if you want via this. we are going to be using TensorFlow for the application and models that we're using. So that's already selected for us as a default. We have a small container size. We don't need anything bigger than that. It's not going to be running a huge production workload. So we'll click on Start Server. And as you can see, starting the server is a fairly simple process. It pulls in a few containers that it needs, runs through the process of installing that on the nodes that are available underneath. And one of the great things about running on ROSA is the fact that if you set it to auto scaling, this will allow the cluster to grow as your teams need and add new nodes when required, so that you never have a blockage. You're never waiting for an infrastructure team to install stuff for you. So there we go. That's all installed for us. We're going to click Open in a new tab. Once again, we'll log in, cluster admin, log in. Thank you very much. We're having to give permission back to the account. So we'll allow the selected permissions. And our Jupyter notebook is up and running. As you can see, the notebook is running Python 3.914. You can open a console, and there's various other bits and pieces that you would expect around a notebook, terminal, text file, and stuff like that. To make this useful, we are going to shortcut the process and use something that's already been built. So we'll pull that from Git, much like some of your developers and your teams would, and we're going to click Clone a repository. Let me just grab the URL for that. Copy and paste that in, and we will hit clone. Takes a couple of seconds to come down, and we drop back into the folder mode. And as you can see, we've now got object detection rest. So if I double click on that, we'll jump into that folder. So this is all the code I've just pulled down. There's various folders and files within there. IPYMB are Python-based notebook files, and they're the things that we're going to work through. In case you've never seen a Jupyter notebook before, it is basically a set of cells. Some of the cells can have Python code in, some of the cells will have text in. A cell with Python code in, if you click the run button, it'll actually process the Python in that cell for you, and it allows you to store variables, and you can pass them all the way down the page. So first thing we're going to do is we're going to jump into the Explore notebook. Now, this is the kind of path that your developers would take. They have a data set, they might already have a model, and they want to work on it to understand what's there. So they can set up this notebook, and these notebooks can be shared with the team, and the text can give them information to describe what they're doing and what they're hoping to get. So if you click on play, first thing we're going to do is we're going to import some libraries. So you might see some warnings flash up like this, and that will depend upon how the model was set up, whether it's using GPU or CPU. In our case, we know that this is perfectly fine. The next thing we need to do is pull some information from from S3. So that'll include importing the AWS Python library Boto3 and a few other bits that we need. And we've imported the S3 libraries. We're now going to download an image that we're going to do a lot of our testing on. So we've clicked that. It takes a little while to download, but as you can see, suddenly we have this image has appeared within our file system. We now need to import this into our code. And there's a picture of two pretty dogs. So if we click next, we'll load that image in, and it's now loaded as a function. We will then start the tensor process. What we're doing here is allowing the image to be processed by TensorFlow, giving it the various bits of metadata that we need. The next thing we're going to do is we're going to load in the model. This model has been pre-created. It is the SSD MobileNet v21 that is on the TensorFlow hub, and it has been trained against Google's OpenImages v4. So we'll pull that model in and start to process against the tensor data of the image that we've created. So here we go. as it starts to spit out bits of information for us. Takes a few seconds to run. Obviously we could have stuck a bigger container in there, or a bit more memory, a bit more CPU, and it might have worked a bit quicker, but as you can see, it's a fairly fast model with a fairly fast processing. As you can see, it's returned some information as well, which is all very useful, but unless you're a trained data scientist and you know exactly what's going on here, this most probably means very little to you, and certainly isn't very quick and easy to understand. So what we can do is we can spend some time developing our application to take that data and display it in a better way. So as you can see, we will have worked through the Python code here that will allow us to define the image and take that information that the model has given us to be able to display it over the top of the image. And here we go. We come out, as you can see, the two dogs are very clearly highlighted, but then there's lots of other things in the background that are calling out footwear. Maybe you wouldn't want that. So let's have a look at the results. We've actually got the detection scores, and the confidence is a key thing when you're looking at data models and image analysis. So anything that is 1 is 100%, but the closer to that number, the more confident the model is. We've got an 84 and a 79, which are very clearly the dogs, and then you've got other lower things. So some of the way to filter out the noise that we would consider footwear to be in this case is that you can actually set your minimum confidence level and how you'd like that to display. So we'll run that now, and we've set a 30% confidence level, and as you can see, that clears up the image. So what we've done here is basically we've taken an image, we've got our model, and we have iterated through, used this notebook to give us an idea of how we can write an application to display the information that is sent back to us from the model. That would allow people to work very quickly. Removes the not on my machine. It means the fact that, like I said earlier, your teams have an environment that can scale based on their needs. Because it's out in your environment, it's obviously a lot more secure. So the idea is it removes the need from using local machines, but giving the developers the same kind of access they would if they were developing locally, but on your environment with the power behind it to do it quickly. So we've explored that. Next thing we need to do is we need to serve that model and be able to allow other people to consume it. So what we want to do is take our exploration and move that into being an actual application that we can allow others to access without the need to understand the underlying model. So we can move that code into a more robust application status. So if you have a look at what we've got various bits and pieces going on within here, and we need to convert our test code into running as an application. There's a requirements.txt file here, and as you can see, we can open these text files as well, and this is going to tell the Python application or the Python environment what it needs to install to be able to run. So if we kick off that and come down there, you'll notice that it has done exactly the same as if you were doing a pip install against a requirements file. It's pulled down everything that's needed. We need the prediction function, which is important in TensorFlow, base64, which is how the image gets uploaded, and it works on paths within the OS. So this then sets up a bunch of functions. Running through the process, same errors as we've seen before. Now we're going to take this code that we believe is good enough from Explore, and we're going to test that it works, just to confirm, just like you would with any other application development. you do a level of test-driven development. This will allow us to be able to test that this code, these functions above, are working as expected. And as you can see, it drops out information with bounding boxes. Footwear, dog. So you've got your class, your label, your bounding box information and things like that. So we want to check now that we can actually visualize those results that get sent back. And as you can see, we have our image. So we want to be able to extract the prediction into the file. Let's test that. Takes a few seconds. Boom, there we go. So it gives us the information and it gives us the image as well. So we can be pretty confident that the code that we initially played with there and that we have extracted now into our Python file is good enough for us to be able to serve as a Flask application. So let's try running it in Flask. As you can see, it knows from the last time we've already run this. We'll double check. Thank you very much. Certainly has. We'll hit run again. So this is now kicking off our Flask app for us to be able to double check as it would be delivered that it is all going to work correctly. Okay, so you can see this is a development server. This is not good for using in a production. Use the WSGI environment. And it's running on a local server. So let's jump into Notebook 4. And this will allow us to directly test the Flask app. So the first thing we will do is we'll import the image that we downloaded earlier. We have our root set in there and we'll set that up. Status OK. We know, because this tells us that if you hit status, it brings back or should bring back status OK if the app is running correctly. The next thing we're going to do is pass into predictions, and predictions is the bit that takes the data, takes the body and passes it into the application that we've just created. So if we run that, up comes with the detections. Let's now pass in the image to see what we get back, the bounding box, and let's run this to see if it will return what we expect. We're now very confident that our notebooks, through the, from our first explorations to building our function to wrapping it within Flask, that we can deploy this very easily for others to consume as an API. This is where running on this kind of environment makes things a lot quicker. What we can now do is jump back in to our OpenShift console. We're in the administrator overview there, but let's click in developer. Normally, not everybody would be set up as an administrator, so they would come into this environment more likely first off. So we're going to move up to add, but we are going to create a project and we're going to call it object detection rest. Oh, let's call it object detection just for ease. Keep it consistent. We will copy that, or we'll paste that, and we'll hit create on that. Our code came from Git, but if we were still in this environment and we'd done all this development, we would have pushed it back up to Git to make sure it was safe. So what we're going to do is we're going to click import from Git, and we're going to copy our Git URL in. Paste on that, and you can see it runs off and says it's validating. And it comes back to us, it understands that it is a Python environment. So it knows the underlying container that it needs to be able to build this application. We're going to tweak some stuff to make it seem cleaner. So we're going to call it object detection REST. It's just, application name and REST. Yeah, I'm going to delete that as well, so that's nice and clean. Deployment type, yes, we'll leave it on the target port as it is. And what we will do, it might need a bit more beef than the cluster allows us. So what we will do is we will click on resource limits and we'll tweak this a bit. We will make sure it has a minimum of a half a CPU up to a maximum of a full CPU, and we'll give it plenty of memory without making sure that it doesn't pull the entire cluster down. And we'll hit create. As you can see, we've just kicked off a process. It says resource added, deployment created successfully. And in the topology window that we've got, you've got the name of the application, and you've got various links on it. If we click on this, you'll see that it pops up what is happening on the side. And you've got various tabs you can look at within here. It's scaling to 1, it tells us, all the labels that go with it. Maximum surge, various bits of information. We've all left these as default, but you could be tweaking this as part of your deployment. Resources, so it's waiting for the build. At this moment in time, you can see it's kicking off there. If we click on view logs, you will see that it's actually cloned down the repo that's needed. It is now pulling in everything from requirements.txt, exactly the same as you saw within the Jupyter notebook, and basically wrapping up the entire environment. If we go back to topology, click on here. At the moment, it's still building the container that we require to be able to deliver the application. So we'll jump back once it's up and running. And we're back. So that took about 4 to 5 minutes for a complete build, deployment, and opening up the routes to get there. If we now click on the routes, which is the URL into the application itself, if we click on that, as you can see, that's generally a slash. So it's bringing us back the status OK. So you might think, how can I easily test this? If we take this and we copy, we can jump back into our original test Flask application. And if we change my route, so now we've set this up where my route is actually pointing out to the public endpoint of our cluster. So we'll set that, which will update the variable there. We get the status OK back. We pass in the image, we get the detection back. Okay, we seem to have the bounding boxes. And bingo, it comes back with exactly what we saw earlier. So how can we truly check that that is exactly what is running? So let's do another test that should show us if this is really working in the way that we expect. And if we take a local image I've got, cat, and we change my image to cat.jpg. Let's run that again. Okay, different bounding boxes this time. So we can see our cat image and the cat is getting picked up. And as you can see, that has been passed into the external application. So you know your API is working fine. How about we deploy an application just to demonstrate once again how quick and easy it is to do this. If we go back into our cluster and we will click add, import from Git, we'll grab another quick URL and that runs off, and you notice this time it's understood it's a Node.js application. What we need to do is to change this to app. We'll group it with the REST app. And here we need to add deployment information. And what we need to add is an environmental variable that tells the app where it needs to look to get the information. If we click on create, once again this will take a little bit of time. Following the same process, it'll build the application and stick it in an appropriate container, and then push that container to the internal registry that will then deploy the application. It'll then be pulled from that environment into our environment and opened up to the world. So the application is built, it's opening the URL, it's allowed to use my camera, and as you can see, it's done that on the fly. Thank you.